Hello and welcome to Lesson 6 of Counting Probability or Combinatorics. Today we're going to be discussing a lot of topics, and all the topics are connected because they're all probability. So let's get started. So this isn't really much of a change from counting, because many probability questions are just counting problems. So before we get to any specific problems, let's just look at what probability is. Unfortunately, it's kind of hard to define probability without just saying probability is the chance of something happening. And what is the chance? Well, it's the probability. So let's instead start with an example. Let's say we're flipping a coin. We can either get heads or tails, and we just want to find out the probability of getting heads. So there's one way we get heads out of two options. So there's a 1 out of 2 or 50%. It's just two counting problems. And we just solve that by saying the number of successes over the total possibilities. And what's very important to note here is that all possibilities are equal. Heads and tails are equal. If heads was 2 times as much likely, then we might want to count it as 3 cases. Heads, heads, or tails. So some things you might want to know is that 0 means impossible, 0.5 means as likely as not, and 1 means guaranteed. Some topics we're going to be covering are basic probability, addition with probability, complementary probabilities, multiplication with probabilities, and probability with dependent events, and as well as topics in geometric probability, which is probability using lengths or areas. So without further ado, let's get started. The faces of a fair six-sided die are numbered 1 through 6. What is the probability that when it is rolled, a 2 is facing up? When we roll the die, there are 6 equally likely outcomes. A 1, a 2, a 3, and so on, all the way to a 6. In this problem, there is only one successful outcome, namely a 2. So the probability that a 2 occurs is just one successful outcome divided by 6 total possibilities, or 1 out of 6. The way we can interpret this is if you were to roll our dice many times, we would expect about 1/6 of our probability of our rolls to come up heads. We might write this as P of 2 is equal to 1/6, which is saying the probability of a 2 is 1/6. So now let's go into a more complicated problem. A standard deck of cards has 52 cards divided into 4 suits, each of which has 13 cards. 2 of the suits, hearts and diamonds, are red, and the other 2, spades and clubs, are black. The cards in the deck are placed in random order, usually by a process called shuffling. What is the probability that the first 2 cards are both red? Since all choices for the first 2 cards are equally likely, we need to count the total number of possibilities and also the number of ways that both can be red. So it's just our success over total formula. For the total number of possibilities, there are 52 ways to pick the first card and 51 ways to pick the second card. So there's 52 into 51. For the number of successful outcomes, there is 26 into 25. Because that's the way you pick the first red card, and that's the way you pick the second. Simplifying this or multiplying this out and simplifying gives you 25 over 102, which is about 25%. It's more closer to 24 and a half, but that rounds to 25. Suppose two distinct odd integers are chosen from 1 through 9. Wait, sorry. Suppose two distinct integers are chosen from between 1 to 9 inclusive. What is the probability that they're both odd? Well, in order to solve this problem, we have to determine what the equally likely outcomes are. So we can just say the number, we have to choose two numbers, but there's two ways we can count it. We can either say order matters or order doesn't. But we can show that they both give the same answer. Let's say order does matter. Well, in that case, how many ways can we pick two integers from 1 through 9? That is just 9 times 8. And how many ways can you pick two odd numbers? That is 5 times 4. And this entire thing simplifies to 5 over 18. What if order doesn't matter? Well, in that case, how many ways can you pick two numbers? If I choose 2. How many ways can we, how many ways can you pick two odd numbers? If I choose 2. How many ways can we pick two numbers in that range? 9 choose 2. This gives us 10 over 36, which is still equal to 5 over 18. So both of these give the same answer. Remember, don't compare apples to oranges. Don't say, well, there are 9 choose 2 ways to pick two numbers, and there's 5 times 4 ways to pick two odd numbers. Well, right now we're saying order does matter, and here we're saying order doesn't. So you're kind of just comparing apples to oranges, and you would get something weird like 5 nights, which is not our answer. So remember to stay consistent are using does order matter or does order not matter. When rolling a fair 6-sided dice, what is the probability that a 2 or a 4 is rolled? Well, there's a few ways to solve. We can just state the obvious. There are 6 total equally likely outcomes and 2 successful ones, so 1/3. Or we can go like the probability of, well, we know it's 1/3. And we might notice that a probability that a 2 or a 4 is equal to the probability of a 2 plus a 4. So this is actually true because they're mutually exclusive, which means that the probability of both of them occurring is equal to 0. In this case, they are mutually exclusive. So we have the problem. A card is chosen at random from a standard deck of 52 cards. What is the probability that the card is a queen or a diamond or both? So what we might think is there's 4 ways to pick a queen, there's 13 ways to pick a diamond, and there's 52 total cards. So therefore our answer is 17 over 52. But I'll show you why this is wrong. There are 4 ways to choose a queen, and there are 13 ways to choose a diamond, but both outcomes are not mutually exclusive. We might pick a queen of diamonds, which belongs to both outcomes. So we have to subtract 1 to do this over counting. So we get 4 plus 13 minus 1, which gives you 16 out of 52, or 4/13. You can also set this up as probabilities. The probability of the probability of A or B is equal to the probability of A plus the probability of B subtracted the probability of A and B. And this formula works for everything. We can say, what is the probability of queen? That is 452. What is the probability of diamond? That's 13 over 52. And what is the probability of both? 1 over 52. And we'd get the same thing. So this is kind of a really tedious problem. So let's quickly get into this. A bag has 3 red and k white marbles, where k is an unknown positive integer. 2 of the marbles are chosen at random from the bag. What is the probability, given the probability that the 2 marbles are the same color is 1/2, find k. So we begin by noting that both of these are mutually exclusive. So that means p of both is equal to the sum of p of red plus the sum of p of white. P of red is equal to, how many ways can we pick 2 red things? 3 choose 2 over k plus 3 choose 2. And the probability, which is equal to 3 over k plus 3 choose 2. What is the probability that both of them are white? So white. That is equal to k choose 2 over k plus 3 choose 2. Which is equal, which can't be simplified. Which means the probability of both, which is equal to 3 plus k choose 2 over k plus 3 choose 2 is equal to 1/2. Okay, if we expand everything, we get 3 plus k into k minus 1 over 2, entire thing over k plus 3 into k plus 2, entire thing over 2, and that's equal to 1/2. If we simplify this a lot by cross multiplying and then simplifying further, you get 12 plus 2k, k minus 1, is equal to k plus 3 into k plus 2. And expanding everything and then subtracting everything to one side gives you k squared minus 7k plus 6 equals 0. You can try multiplying all of this out and simplifying it yourself to get this, but it's a lot of messy algebra. This factors to x minus 6 into x minus 1 is equal to 0, which means k is equal to 6 or 1. And both work. Notice that this solution used a lot of algebra. Many probability problems require a bit of algebra to work through, so yeah. And combining counting techniques to simplify algebra is a powerful problem-solving technique. Note that we could have solved the problem by calculating the total number of successful outcomes instead of the total probabilities, and then adding them together and dividing by this total instead of doing it the way we did. Both of them still end up at the same, so yeah. Next problem. Now we're going to go to an easier note. What is the probability that it will rain tomorrow plus the probability that it will not rain tomorrow? The event it will rain tomorrow and the event it will not rain tomorrow are exclusive events, meaning it can't both rain and not rain. And these events are exclusive in an even more powerful way. Either one or the other must happen. Either it has to rain or it won't. So we could say that the sum is equal to 1, because it's guaranteed for one of the two things to happen. More generally, if A is any event, then the probability that A occurs plus the probability that it doesn't is equal to 1. Usually this is kind of useless by itself, but if you write it in the way probability of A doesn't occur is equal to 1 minus the probability of A occurring. These are called complementary probabilities. Often, if it's easier to calculate the probability of something not occurring than it is to calculate the probability of something occurring. And a good example to show this is, what is the probability that when we roll a 4 fair 6-sided dice, they won't all show the same number? Well, it's kind of complicated to calculate, well, what if this is this and this is this? Well, there's a lot of different cases. But what we could do is say, well, what is the probability that all of them show the same number? Well, in that case, there's 6 for the first one and 1 for each of the other ones. And how many total possibilities are there? That's 6 to the power of 4. This gets 1/6 over 6 cubed. And the probability that this does not happen is 1 over this, which is equal to 215 over 260. A notation that commonly gets used is P of A prime, which basically means the probability of A not occurring. Now let's get into multiplication with probabilities. 2 6-sided dice are rolled, 1 red and 1 green. What is the probability that the red dice shows a 2 and the green dice shows a 5? Well, we can just say how many total possibilities there are, which is 36, and there's only one possibility where this happens. What we can also do is multiply them together, because adding led to ORs, so maybe and is multiplication. So 1/6 squared ends up giving 1 over 36. So maybe this is true generally. Maybe P of A and B is equal to P of A times P of B. Maybe. Well, this is actually only true if it's independent. Dependent, it gets slightly weird. So let's deal with another independent thing before going into dependent stuff. The Grunters play the Screamers 4 times. Weird names. The Grunters are a much better team and are 75% likely to win any given game. What is the probability that the Grunters will win all 4 of them? Well, there's 4 games, so it's just 3/4 times 3/4 4 times, or 3/4 to the power of 4. This is equal to 81 over 256. But what if they are dependent? What if one does depend on the other one? Now what? Well, in this case, we can say, how many ways can the first card be a diamond? Well, it's 13 out of 52. And how many ways can the second card be a spade? Well, assuming the first card's already a diamond. Well, in that case, it's 13 over 51. Therefore, our answer is 169 over 51 over 52. 51 into 52 which is 2652, or 13 over 204. Understand why each of them are not 1/4. It's not just 1/16. It is 13 over 204. So now another problem. A bag has 4 red and 6 blue marbles. A marble is selected and not replaced, and then a second is selected. What is the probability that both of them are the same color? So the probability that of same color is the probability that both of them are red plus the probability that both of them are blue. The probability that both of them are red is just the probability that the first is red and the second is red after the first red is drawn. And the same thing for blue. So the probability of both being red is equal to 4/10 times 3/9, which is 2/15. And the probability that two of them are blue is equal to 6/10 times 5/9, which is equal to 1/3. Adding these two together gives 7/15. So the probability that both of them are the same color is 7 out of 15. So I don't know what happened, but the image is kind of squished. So let's go over it. This is a pretty hard problem, so yeah. Becky lives in a place with a very clear sky. On Friday night, there is a 60% chance that she'll see a shooting star in any given hour. If Becky goes outside and watches the sky for 2 hours, what is the probability that she'll see a shooting star? Well, you could do casework and go like, well, the probability that she sees it in the first hour and not in the second is 60% into 40%, and then so on and so forth. But we can use complementary probabilities. What's the probability that she does not see it at all? Well, that is just 40% squared, which is equal to 0.16. And 1 minus that is equal to 0.84. So the probability that you'll see a shooting star is 84%. We're giving percent, not a fraction, because all the numbers we were given are also in percentage. Well, that problem wasn't really that bad. I used the same techniques that we've been using throughout this entire thing. So, what about the second part? Still kind of squished, so I'm going to read. On Saturday night, Becky will again go stargazing. This time, conditions are better and there'll be an 80% chance that she'll see a shooting star in any given hour. We assume that the probability of seeing a shooting star is uniform for the full hour. What is the probability that Bessie will see a shooting star in the first 15 minutes? Well, first, you just understand why the problem is not just 20, 1/4 of the probability. In the previous thing, it ended up being 84 and not that. It's like if you multiplied it outright, it's like saying for the previous thing that 60% chance for 1 hour, it's 120 for 2 hours, which is obviously not correct. So what do? Do we have to do casework? Well, case 1, Bessie sees a star at all 4 hours. Well then, p to the power of 4. If p is the probability of us finding in the first hour, or seeing in the first 15 minutes. Case 2, well now you got 4p cubed 1 minus p if she sees it in 3 of the 4. But this is a lot of work. What you can do is go back to complementary powers. It's really hard to count what we do want to know, so why don't we count what we don't? So, what is the probability that she does not see it at all? It's just 1 minus p to the power of 4. And the probability that she does not see it at all is 20%, because there's an 80% chance that she does see it. So now, solving for p, you get 1 minus p equals 1 over the 4th root of 5, and p is equal to 1 minus 1 over the 4th root of 5. And this is equal to about 0.331, or there's going to be a 33.1 chance that she sees it in the first 15 minutes. Well, now we go to geometric probability. So let's start with a crash course. Earlier we had discrete values, which means that you can count individual things. It's 1, 2, 3. But what if there's infinite things? What if we get something like we have a square? What is the probability that it is in the bottom left quadrant of the square if you pick a random point in it? Well, there's infinite positions for the points, so what do we do? So you might have seen earlier that what we do is say, instead of probability of success over probability of total, is just size of success over size of total. And now we can deal with continuous stuff. So you might have seen this asterisk around impossible and guaranteed. Well, here's why. Imagine we're throwing a dart, and the dart lands on a single point. What's the probability that you hit that exact point, not even a millimeter off the next thing? Well, it's infinite points. And if you calculate the probability, it's 1 over infinity. And you can't just plug in infinity. So let's just say 1 over 100, and you just keep adding zeros. And you get a practically zero number. And it's the exact same as 0. So when it says 0, it doesn't mean it's impossible. It means it's basically never gonna happen. And what about the probability of hitting everything except that? It's technically probable to hit that, but you're probably not gonna hit it. So it's technically guaranteed that you don't hit that same point again. So that's why those asterisks are there. Geometric probability is kind of vague, but hopefully this problem will try to help you better appreciate it. Geometric probability also gives us important probability tools. We can often represent a non-geometric problem in terms of geometry, which we can then use to calculate probability. So let's solve this problem. First, let's determine the region in which the condition is satisfied. In other words, we say, what regions are the points closer to B than they are to A? Well, on this line, the things that are closer to B than they are to A is, let's quickly just draw that. Actually, it's a line segment. Okay? And you got B somewhere here. The things that are closer to A than they are to B is anything in this range. And anything that's closer to B is in this range. Well, you might realize that here's the numbers for the lengths. 2, 2, 1. And if you want to see when it's closer to B than it is to A, the total length of the blue area is 3, and the total length of the entire line is 5. So you get 3/5, which is our answer. One thing to note regarding the solution is that measuring the successful region, the point D does not actually contribute anything. So it's okay to use the length of DC as our size of the successful region, because a point is practically 0. So now let's go to areas. How to do probability with areas. Well, point C is chosen at random on top of a 5 foot by 5 foot square table. A circular disc with a radius of 1 foot is placed on it, with the center directly on point C. What is the probability that the entire disc is on top of the table? That means none of the disc is hanging over the edge. Well, the total outcome is easy. It's just a square. 5 by 5 square, actually. The total outcome regions is easy, but the successful is kind of hard. We can see that the disk will be entirely on the table if and only if C is at least 1 foot away from the edge of the table. So it would be in something like this, where we got 3 by 3 square. And now we see that the probability that's in the square, which is the success, is 9, the area of it, over 25, the area of the outside. So that's kind of how you use area. Let's try to use, because area is really useful as a probability tool. So let's see an example of it being put to work. My friend and I are hoping to meet for lunch. We'll each arrive at our favorite restaurant at a random time between noon and 1 p.m., stay for 15 minutes, and then leave. What's the probability that we meet each other while at the restaurant? For example, if I show up at 12:10 and my friend shows up at 12:15, we'll meet. But if I show up at 12:50 and my friend shows at 12:20, we'll miss each other. Once again, because we have infinitely many possibilities, you can go at 12:10 in 10 seconds, you can go 12:10 in 10.5 seconds. We're going to use geometry. Let's create like a sort of graph for the possibilities. This is 12 o'clock, this is 1 o'clock, and the same thing for the other side. This is your arrival, and this is your friend. So if you arrive at 12, that means your friend can arrive from 12 to 12:15. If you arrive at 12:10, your friend can arrive at 12 to 12:25. If you arrive at 12:20, then now it's 12:05 to 12:35, and so on. Just by like sketching that, you kind of get an idea of how the graph looks. And it looks something like this. And normally the 1 would be somewhere around here, but my thing is not up to scale. So it would look more like this. Where this is around 1. So now we want to find the area of this region, divided by the area of the entire thing, which is 1 by 1. Well, this is kind of hard to do. It's like a really weird shape. But what we can do is complementary probabilities, but in geometry. We count what is not what we want, these two things. And the area of both of them are 20/25, assuming that this entire thing is 60 by 60. If you're partitioning it in minutes, it would be 20/25. And the total area is 3600, 60 times 60. Dividing that entire thing by 3600, you get 1575 over 3600, or 7 over 16. So the probability that you meet is 7 out of 16. So this was a pretty long video, and we went over a lot of topics. So let's just do a final recap. In probability, we discussed what are probabilities, how to turn them into counting problems. We went over basic probability problems, how to use addition to do ORs, complementary probabilities, how to use multiplication for ands, and how to do probability with dependent events, probably using lengths and areas, and as well as some special cases like impossible or really, really unlikely, or guaranteed or almost always. And yeah, I hope you learned something. Have a nice day. Advik.